It began long before anyone boarded Flight 191, before the passengers packed their suitcases, before the crew stepped into the cockpit, before the DC-10 even rolled onto the ramp at Chicago O'Hare. The chain reaction that would lead to the deadliest single aircraft crash in American history didn't start with a dramatic failure or a fiery explosion. It started quietly, almost invisibly, with a maintenance decision made 4 years earlier. A decision that seemed harmless, even practical, yet carried within it the seeds of catastrophe. In May of 1975, McDonnell Douglas issued a service bulletin for the DC-10 fleet. It wasn't alarming. It wasn't urgent. It simply recommended replacing certain spherical bearings inside the aft pylon, the steel structure that held each of the aircraft's wing-mounted engines. For most people, this would sound like a minor technicality, but in aviation, tiny details often hold enormous power. And on the DC-10, the integrity of the pylon was everything. It carried tens of thousands of pounds of thrust, vibration, aerodynamic stress, and torque. If anything went wrong there, the consequences could be immediate and brutal. The bulletin wasn't mandatory. Airlines could perform the work during scheduled heavy maintenance checks, C-checks, as they were known. That meant months, or years, might pass before a given aircraft underwent the modification. This wasn't unusual. In the 1970s, non-critical bulletins were part of everyday operations. But this particular recommendation intersected with another dynamic unfolding inside American Airlines and other major DC-10 operators: the constant pressure to reduce downtime, cut costs, and streamline maintenance. At the time, removing a DC-10 engine for servicing was a major undertaking. The official McDonnell Douglas procedure required technicians to detach the engine from the pylon first, then lower the pylon itself from the wing. Two separate operations, two sets of tools, two teams, and hundreds of labor hours. For airlines operating dozens of DC-10s, that meant millions in annual maintenance expenses. So American Airlines, Continental, and to some extent, United Airlines began to wonder, why not remove the engine and the pylon together, as one piece? The idea wasn't reckless, at least not at first glance. It promised to save nearly 200 man-hours per aircraft, reduce the number of hydraulic and electrical connections technicians had to detach, and minimize human error during reinstallation. Fewer connections meant fewer chances of miswiring something critical. But McDonnell Douglas engineers weren't convinced. When the airlines asked for an evaluation, the manufacturer reviewed the proposed method, lifting the engine-pylon assembly with a heavy industrial forklift, and immediately spotted potential problems. The engine's center of gravity was awkward. The forklift's control precision was limited. Even slight misalignment could shift thousands of pounds of metal by inches, enough to bend, scrape, or stress components not designed to bear such loads. The manufacturer couldn't forbid the method, though. Under U.S. regulations at the time, the FAA delegated substantial oversight authority to airline internal inspectors. If an airline believed a new maintenance procedure was safe, there were few barriers to adopting it. And so, in maintenance hangars across the United States, the new technique spread. Engines were left attached to pylons, suspended on forklifts, while crews worked to unbolt the assembly from the wing. It was delicate work, so delicate that even a half-inch movement of the forklift's forks could induce dangerous pressure on the pylon's mounting points. Technicians had to rely on hand signals, watching for tiny shifts while coordinating with operators who often couldn't see the critical areas themselves. Warnings came early, but they were missed. Twice, Continental Airlines mechanics reported damage to DC-10 pylon components during this procedure. But instead of prompting a re-evaluation, the incidents were logged simply as maintenance errors, human mistakes. No one considered that the method itself might be inherently flawed. The American Airlines DC-10 that would later operate Flight 191 arrived at the Tulsa maintenance base in March 1979 for its scheduled work, including the pylon modification. What happened there over the next 3 days would quietly seal its fate. From the beginning, the job went poorly. The night shift struggled to separate the pylon from its wing mounts. Bolts that should have released smoothly refused to budge. Instead of following the recommended sequence, detaching the forward mount first, technicians removed the aft mount instead, creating a pivot point that allowed the engine and pylon to shift. When the day shift came in, they found the aft pylon bracket pressed against the wing surface, something that should never happen under normal conditions. Attempts to realign the assembly were interrupted when the forklift ran out of fuel, freezing the engine pylon unit in an unstable position. No one noticed the tiny stretch fracture forming in the metal of the aft bulkhead's forward flange, a fracture caused by the upward pressure exerted by the misaligned assembly. It was invisible to the naked eye, hidden under paint, masked by normal wear. But in aviation, a fracture doesn't stay small for long. Over the next 8 weeks, as the aircraft flew hundreds of takeoffs and landings, the forces on that weakened flange grew. Metal fatigued. The fracture spread. And the pylon that held the left engine, an engine weighing nearly 18,000 pounds, slowly crept closer to failure. Passengers booking tickets for Chicago to Los Angeles had no way of knowing that their fate was already intertwined with a moment in a hangar, months earlier, when a forklift drifted an inch too high. Engineers at McDonnell Douglas couldn't see it. The FAA couldn't see it. Even the mechanics doing the work likely had no idea of the danger that had been set in motion. Yet the story of Flight 191 truly began there, in silence, in routine, in the subtle compromise between cost savings and safety, a compromise that would only reveal its consequences in the most violent way imaginable. The new maintenance procedure, removing the DC-10's engine and pylon as a single unit, was supposed to make things easier, faster, more efficient. In the minds of airline executives in the late 1970s, it was the kind of innovation that kept fleets running and kept costs under control. But inside the hangars, among the men who actually had to perform the work, the method revealed itself as something very different. A delicate, unforgiving balancing act where a single misalignment could quietly damage a structure never meant to be stressed in such a way. By the time American Airlines committed fully to the forklift method, the risks had already begun to materialize. Mechanics quickly learned that placing the forklift beneath the engine demanded near-perfect accuracy. Being off by even a couple of centimeters could shift thousands of pounds of metal in unpredictable ways. The engine was long, heavy, and forward biased. The pylon was narrower, lighter, and attached underneath the wing at an awkward angle. Keeping this combined assembly balanced on a set of steel forks required precision normally reserved for surgical instruments, not industrial machinery. Operators sat inside their forklifts with almost no view of what mattered. The critical connection points, the forward and aft pylon mounts, were several feet above their line of sight. They had to rely entirely on hand signals given by spotters who stood near the wing, watching for the slightest movement. A gesture to lower or tilt back might translate to a mechanical adjustment that moved the engine an inch, maybe 2. And even a single inch could put pressure on the pylon attachments that the aircraft's designers never intended. At Continental Airlines, problems appeared early. On 2 separate occasions, technicians damaged the aft pylon fitting while performing this streamlined procedure. Each time, the damage was written up as human error, the result of someone being careless or misjudging the forklift's position. The incidents were not escalated. They were not analyzed in depth. The procedure itself was never questioned. After all, the airlines were saving time, saving labor, and saving money. Why dig deeper? But the truth was becoming impossible to ignore, at least for those working closest to the aircraft. The forklift method was inherently unstable. Unlike an overhead crane used by United Airlines, which suspended the engine assembly from above, the forklift supported the massive weight from below, where even minor vertical drift produced enormous leverage against the pylon's mounting flanges. The slightest bump of the forklift's hydraulic controls could force the assembly upward into the wing. The slightest drop could strain the forward mount like a crowbar being pulled away from a hinge. Yet, in the 1970s, the regulatory environment allowed airlines wide discretion over their maintenance practices. The FAA, stretched thin by rapid airline expansion, delegated much of its oversight authority to the airlines themselves. Internal inspectors, employees of the companies they were expected to oversee, reviewed and approved procedural changes. This system worked well enough when airlines chose caution over efficiency, but in this case, it left a critical gap, a blind spot wide enough for disaster to slip through. In late March 1979, when the accident aircraft was rolled into the maintenance bay in Tulsa, that blind spot became deadly. The team assigned to remove the engine and pylon from the left wing had no reason to suspect that the procedure itself was dangerous. They had no directive from McDonnell Douglas, no warning from the FAA, no data suggesting they were working with a flawed method. To them, it was just another job, a difficult one, yes, but nothing out of the ordinary. Still, the work immediately resisted them. The bolts on the forward pylon fitting were stubborn, refusing to release even under steady pressure. Instead of halting the job or revisiting the recommended sequence, the night crew made a decision that seemed small at the time. They detached the aft fitting first. It was a shortcut, a workaround, the kind of improvisation that happens when people believe the job must be completed no matter what. That choice transformed the pylon into a lever, pivoting on the forward mount. When the forklift operator adjusted the height, even slightly, the aft end of the assembly could rise or fall enough to bump against the wing, and bump it did. The next shift discovered the aft mount pressed directly against the underside of the wing, a sign that the engine had likely moved upward several inches. They tried again to free the forward mount. They nudged the forklift. They tried to realign the assembly. And then, astonishingly, the forklift ran out of fuel. The engine and pylon, together weighing more than 8 tons, hung suspended in an unstable position while workers scrambled to restart the machine. No one could know precisely when the damage occurred. Whether it was during the shift change, the repeated attempts at realignment, or the moment the forklift sagged on empty hydraulics, the result was the same. A small but fatal stretch fracture formed on the forward flange of the aft bulkhead attachment, a fracture invisible beneath layers of paint and grime, a fracture that no inspection detected before the aircraft was released back into service. Over the next 2 months, that microscopic wound grew. With every takeoff thrust, every landing impact, every vibration, the fracture lengthened, slowly, silently. The pylon, once designed to withstand enormous forces, now carried its load on compromised metal. Meanwhile, in conference rooms and offices far from the hangar floor, decision-makers had no idea what was happening. They believed the forklift method was working. They believed they had found a clever way to make maintenance more efficient. The 2 earlier Continental incidents, buried under the label of technician error, never reached the desks of those who needed to see them. The warning signs scattered across the industry. Technical notes, mechanic complaints, informal conversations never coalesced into a formal alarm. And so, the DC-10 returned to the flight line, its left engine hanging from a damaged pylon, while passengers boarded and disembarked day after day, unaware that the difference between safety and disaster now depended on less than a quarter-inch of cracked metal. When Flight 191 taxied out of Chicago that clear afternoon in May, the catastrophe was already fully in motion. It had been in motion since the moment a maintenance shortcut met an aging design, supported by a regulatory system that trusted airlines to regulate themselves. The aircraft's fate was written not in the cockpit, but on a concrete hangar floor in Tulsa, between a forklift's steel forks and the underside of a wing, where one subtle shift had changed everything. The morning of May 25, 1979, broke clear over Chicago, one of those rare Midwestern spring days when visibility seemed endless and the sky looked almost polished. For most of the 258 passengers scheduled to fly American Airlines Flight 191, it felt like the perfect day to travel. Families heading to California, business travelers bound for meetings, couples beginning vacations, people with ordinary plans, ordinary expectations. None of them had any reason to imagine that their lives were already intersecting with a hidden structural failure that had been quietly growing inside the left wing of the aircraft for nearly 2 months. The DC-10 scheduled for the flight was 7 years old, a workhorse of American's domestic fleet. Its 3-engine configuration, enormous cabin, and strong fuel efficiency made it ideal for routes like Chicago to Los Angeles. In the 1970s, it was the pride of long-haul carriers, sleek, powerful, and modern. The reputation the DC-10 would later earn had not yet settled over the public consciousness like a shadow. On that afternoon, it stood at the gate as confidently as any other wide-body airliner of its era. In the cockpit, Captain Walter Lux prepared for the flight. At 53 years old, Lux was exactly the kind of pilot passengers hoped was seated at the controls, experienced, steady, meticulous. More than 22,000 flight hours lay behind him, including 8 years on the DC-10. He had flown everything from piston-driven Douglas transports to high-performance jets, mastering each with calm professionalism. Ironically, he had not even been scheduled to fly Flight 191 that day. He had been called from standby to replace another captain. But his unscheduled presence would become one of the many haunting details that survivors' families would struggle to reconcile. Beside him sat 49-year-old First Officer James Dillard, another veteran aviator with more than 9,000 hours in the air. He would be flying the aircraft that day, handling the controls while Captain Lux monitored systems and communications. Behind them, flight engineer Alfred Udovich completed the trio. At 59 years old with 15,000 hours of experience and a recent transfer to the DC-10, he carried the responsibility of monitoring the aircraft's vast network of hydraulics, electrics, and fuel systems. The aircraft's logbook that afternoon was clean. No unresolved maintenance items, no warnings. Nothing on paper suggested that anything was wrong, because nothing in the manual could have warned the crew about the fractured metal hidden inside the left pylon. They walked into the cockpit with complete confidence in the machine they were operating. Passengers began boarding around 14:15. Families spread out across the rows, stowing bags, buckling seat belts. A few children pressed their faces against windows, watching other airplanes thunder down the runways in the distance. It was a routine day at O'Hare, busy, noisy, vibrant. When the cabin doors finally closed, there were 258 passengers and 13 crew members aboard, 271 souls. At 14:59, after pushback and clearance, Flight 191 lined up on runway 32R. The winds that day were brisk, 22 knots, gusting from the northeast, but well within limits for a heavy jet. Captain Lux read back the takeoff clearance calmly, and First Officer Dillard brought the throttles forward. The 3 General Electric CF6 engines roared to life, building thrust that vibrated through the entire airframe. Everything about the takeoff roll was ordinary. The aircraft accelerated smoothly. The numbers passed in sequence. 80 knots, V1, then VR. But as the DC-10 hurtled down the runway, it carried with it the consequences of that small, unseen fracture at the pylon's forward flange. During acceleration, aerodynamic forces and vibration intensified. The weakened metal flexed, then flexed again. The fracture widened, micrometer by micrometer, until it reached the point where the structure could no longer bear the load. Just seconds before rotation, the aft mount of the left engine pylon failed completely. Witnesses would later describe seeing a flash of mist erupt from the left wing, hydraulic fluid spraying outward like a white cloud, followed by a violent shudder. The engine, still producing full takeoff thrust, twisted upward with tremendous force. It pivoted on the remaining forward attachment, tore loose, ripped away hydraulic lines and electrical wiring, and then separated entirely. In a horrifying moment captured only by the eyes of onlookers, the 18,000-pound engine flew up and over the wing, tumbling onto the runway behind the aircraft. Inside the cockpit, the violence of the failure would have been immediate and shocking. The pilots would have felt the surge of asymmetric thrust, one engine still pushing hard on the right wing, while the left side suddenly lost all power. First Officer Dillard instinctively maintained control, pushing in right rudder to counter the yaw. He continued to rotate the aircraft, as he had been trained to do. Losing an engine in the seconds before takeoff was one of the most difficult emergencies a pilot could face, but it was also one they practiced for repeatedly. Yet this was no ordinary engine failure. When the engine tore free, it ripped away essential wiring, including those powering the captain's instruments, the cockpit voice recorder, and, critically, the stick shaker on the captain's side, the device that warns pilots of an impending stall. It also destroyed hydraulic lines feeding the leading edge slats on the left wing. With hydraulic pressure gone, those slats slowly retracted under aerodynamic load, pulling the left wing into a configuration the pilots had no way of detecting. From inside the cockpit, the aircraft's behavior would have felt bewildering. Dillard, flying from the right seat, would have seen his instruments functioning normally. He would have seen the flight director commanding the plane to pitch for V2, the target speed for an engine-out climb. But the left wing, stripped of its extended slats, now needed a minimum of 159 knots to maintain lift. The aircraft, obedient to the published procedures, was climbing at 153. 4 knots. 4 knots separated stability from disaster, and no one knew it. The cockpit held no warning, no vibration, no indication of asymmetrical slat retraction. The stall was progressing silently, invisibly, beginning at the outer portion of the left wing, far from the pilot's view. As the aircraft climbed through 300 feet, the left wing began to drop. Dillard countered with aileron. The wing dropped further. He added more input. Still, the wing sank. The DC-10 rolled left at a speed no crew could overpower, 4 degrees per second, then faster. The nose pitched down. The city skyline vanished behind a tilting horizon. The aircraft entered a condition from which recovery was physically impossible, given the forces at play. Only 50 seconds had passed since the takeoff roll began. What passengers felt in those final moments will never be known. What the crew understood in the final seconds is unknowable. But the aircraft's path, recorded by a handful of instruments still functioning, shows a desperate, fading struggle against a force the crew had no chance of recognizing. At 15:03, Flight 191, banking nearly inverted, plunged into an open field just beyond the runway off Des Plaines Road. The impact obliterated the aircraft instantly, killing all 271 people aboard and 2 more on the ground. The force was so violent that debris scattered across a wide arc, igniting fires in a nearby trailer park and reducing the DC-10 to fragments. The worst single aircraft disaster in American history had unfolded in less than a minute. rooted not in pilot error, not in weather, but in a maintenance shortcut taken months earlier in a quiet hangar in Oklahoma. What followed in the seconds after Flight 191 left the ground was not a struggle between skilled pilots and a failing machine. It was a confrontation with forces no human crew could have fully recognized, let alone overcome. The detachment of the left engine had set off a cascade of failures so unusual, so specific, and so brutally timed that even the most experienced aviators would have been effectively blind to the true nature of the danger surrounding them. When the number one engine tore away from the wing, the damage radiated outward through the DC-10 systems like shock waves. Electrical lines powering the captain's instruments were severed instantly. The flight engineer lost key indications. The cockpit voice recorder went silent, starving investigators of what might have been the crew's last insights. But even these losses, serious as they were, paled in comparison to what happened to the leading-edge slats. On the DC-10, those slats, mounted along the front of each wing, were essential during takeoff. They reshaped the airfoil, boosting lift at low speeds. With 3 heavy engines and a wide wingspan, the DC-10 relied on them heavily in the first seconds after liftoff. Under normal conditions, hydraulic pressure held the slats firmly in place. But when the number one engine separated, it tore through 2 of the aircraft's main hydraulic lines. Pressure vanished. On the left wing, with nothing holding them forward, the slats began to retract under aerodynamic forces. The right wing slats stayed fully extended. The left wing slats slid backward. From the cockpit, none of this was visible. There were no warning lights, no annunciators, no system designed to call out asymmetry. More critically, the indicator showing slat position, electrically powered, was dead. The pilots had no way to know their aircraft had become aerodynamically lopsided in the most dangerous possible phase of flight. For the first few moments, the DC-10 still climbed. First Officer James Dillard held the yoke, following the flight director as he had been trained. Pitch for V2, the single-engine safety speed calculated before takeoff. That target was 153 knots. On paper, the number was correct. It was standard. But that number assumed that both wings had full lift-enhancing geometry. It assumed that the slats were where they belonged. They were not. With the left slats retracted, the stall speed on that wing ballooned to approximately 159 knots, 6 knots higher than the speed the aircraft was aiming to fly. This was the heart of the crisis. The published procedure and the crew's training, both perfectly correct in every normal engine-out scenario, were now unintentionally guiding them into an aerodynamic trap. As the aircraft climbed through 300 feet, the first signs of that trap appeared. To the pilots, it likely felt like turbulence, nothing more. A slight left wing dip, a small, unexpected roll. Dillard corrected with aileron. The aircraft responded, but sluggishly. Then the left roll began again, more pronounced this time. He added more input. The plane resisted. What he did not and could not know was that the left wing had begun to stall. On the DC-10's early design, only the captain's control column housed a functioning stick shaker, the physical vibration that warns pilots of an impending stall. That shaker was powered through electrical systems routed near the left engine. When the engine tore away, the wiring ripped out with it. The shaker went dead. The only device the crew had to alert them to the single most dangerous aerodynamic condition an airplane can enter had been silenced at the exact moment they needed it. No vibration, no audio alarm, no warning at all. To Dillard, the airspeed indicator showed a safe number. The right wing felt solid. The flight director commanded the proper pitch. Nothing in his field of vision suggested the aircraft was seconds away from losing control. As the stall deepened, the left wing dropped further. The aircraft began rolling at 4 degrees per second, then 6. The nose eased downward. The horizon tilted wildly. Dillard countered with maximum aileron deflection. He added rudder. He did everything a trained pilot could do. But the moment the left wing crossed beyond its critical angle of attack, the situation became unrecoverable. No amount of pilot skill could overcome the fundamental physics at play. The simulator tests conducted months later proved this with chilling clarity. Crews given the same conditions with a working stall warning recovered. Crews given the same conditions without it, just as Flight 191 faced, lost control every single time. At approximately 15:03, the DC-10 rolled past 90 degrees of bank. Its nose pitched down more than 20 degrees. In those final seconds, the aircraft was almost inverted, a massive transport jet descending helplessly toward the ground in a motion more like a falling object than a flying machine. A photograph taken from a nearby trailer park captured its final attitude, a haunting frozen instant that investigators would later use to determine the position of the slats. The impact was instantaneous and unsurvivable. The aircraft struck an open field just beyond the runway, its left wing low, nose down, engine still producing asymmetric thrust up to the moment of destruction. The explosion obliterated the fuselage, sending debris into a nearby hangar and igniting fires across the surrounding area. The force was so violent that the cockpit and forward cabin vaporized, leaving only fragments of structure and scattered metal where the aircraft had once been. For the crew, there was no chance. For the passengers, the final moments were a blur of motion too rapid for conscious thought. The combination of structural damage, electrical failure, aerodynamic asymmetry, and the absence of a stall warning presented a scenario no training program in the world had ever contemplated. Flight 191 was not lost to a single error. It was lost to a chain of perfect conditions, each one small, each one survivable on its own, that aligned in a way both deadly and invisible. The pilots fought the airplane with discipline and skill until the last possible second. But they were fighting an enemy that the instruments could not reveal, the checklists did not anticipate, and the aircraft itself could not forgive. When investigators from the National Transportation Safety Board arrived at the crash site of Flight 191, they faced a landscape of devastation so complete that it defied immediate understanding. The DC-10 had not simply crashed, it had disintegrated. Pieces of metal, wiring, fabric, and scorched debris were scattered across an open field, tangled with remnants of cars and the ruins of a small hangar that had been obliterated on impact. Smoke drifted upward in thin, uneasy columns. Firefighters moved among the wreckage with a somber efficiency born from training, not hope. There were no survivors. There could not have been. And yet, amid the chaos, investigators knew that somewhere within this heap of twisted aluminum lay the truth. They had seen airline disasters before, but the loss of an entire engine, ripped clean off the wing, was almost unheard of in modern aviation. Engines were designed to stay attached through everything except the most extreme structural failure. Something had gone catastrophically wrong, and the investigators' mission was simple, relentless, and unforgiving. Find out why. The number one engine was discovered almost immediately, resting near the edge of runway 32R, hundreds of feet behind where the aircraft left the ground. Its presence there told a horrifying story even before the first report was drafted. Engines are never supposed to detach, and if they do not fall behind the aircraft, they fall ahead or to the side. For an engine to land behind the point of rotation meant it had torn free before the aircraft ever lifted off. A failure at the most vulnerable moment of flight. As the recovery effort continued, investigators began piecing together fragments of the pylon structure. The aft pylon fitting, a critical component, was found with unmistakable signs of overstress and deformation. But as metallurgists examined the pieces more closely, they found something even more troubling. Signs of progressive cracking, not a sudden overload, not a single catastrophic break, a fatigue fracture. This was the moment when the narrative of Flight 191 shifted. Whatever had caused the engine to separate was not the result of pilot mishandling or a sudden in-flight emergency. It had roots that reached back weeks, perhaps months. Somewhere in the aircraft's maintenance history, something had gone terribly wrong, and no one had noticed. Records soon pointed investigators toward the maintenance facility in Tulsa, Oklahoma, where the aircraft, N110AA, had undergone major work in late March. There, the engine and pylon had been removed using American Airlines' preferred method, lifting the entire assembly with a forklift in one piece. At first glance, it seemed efficient, but the more investigators learned, the more this method appeared to be a slow-motion disaster. As interviews began, mechanics described the forklift procedure with an unsettling mix of confidence and unease. Yes, it saved time. Yes, it reduced the number of reconnections. But they also admitted something else. It was difficult, touchy, easy to mishandle. One mechanic from a different airline, when shown the setup, simply shook his head and said, "You can't do precision work with a forklift." In the weeks following the crash, the NTSB uncovered 2 prior incidents at Continental Airlines, where the same forklift method had damaged the aft pylon fitting. In both cases, the damage had been attributed to technician error rather than procedural flaw. This revelation struck investigators with chilling clarity. If the same rare component had been damaged multiple times under the same method, then the method, not the workers, was to blame. The most damning discovery came next. When the NTSB mandated inspections of all DC-10s whose engines had been removed using the forklift procedure, they found 6 additional aircraft with nearly identical cracks in the same pylon fitting. 6 planes that had flown with hidden damage. 6 potential Flight 191s. This changed everything. The FAA, faced with mounting evidence, grounded all U.S.-registered DC-10s. Other aviation authorities around the world followed suit. The aircraft that once symbolized modern efficiency was now tainted with suspicion, treated as a hazard until proven otherwise. The grounding ignited political controversy, public fear, and fierce debate between regulators, manufacturers, and airlines. Many pointed fingers at McDonnell Douglas, whose DC-10 design had already faced scrutiny after earlier accidents. Others blamed the FAA for lax oversight, but the evidence pointed in a different direction. The pylon itself, investigators concluded, was structurally sound. The design met all certification standards. The problem was not the engineering, it was the unauthorized maintenance technique adopted by airlines. A method that McDonnell Douglas had warned against but could not formally prohibit. A method the FAA had never evaluated. A method that seemed efficient until it quietly fractured the spine of a wing-mounted engine. Still, there were more lessons buried in the wreckage. The investigation exposed another vulnerability: the DC-10's stall warning system. Only one stick shaker, only one set of electrical lines powering it. A single point of failure in a system designed to prevent aerodynamic catastrophe. When the engine severed those wires, the crew lost the only physical warning of an approaching stall. Without that vibration through the yoke, the captain could not feel the subtle aerodynamic cues that might have saved the aircraft. Simulator tests later confirmed this. When pilots had a functioning stick shaker, they recovered. When it was disabled, as it was on Flight 191, they did not. The asymmetry of the slats was another revelation. No warning, no annunciation, no instrument telling pilots that the aircraft's wings were no longer configured equally. Without slat position indicators, disabled along with the left engine electrical bus, the crew unknowingly flew an airplane whose left wing required a higher speed to stay airborne. They flew at the correct procedure speed, but it was the wrong speed for the broken aircraft beneath them. Gradually, the NTSB assembled a picture that was both technically intricate and painfully human. Flight 191 had fallen victim to a chain of events so rare that no single person, no single department, no single oversight mechanism had caught it. Yet every link in that chain was identifiable. A cost-saving maintenance shortcut, a forklift lifting too high, a microscopic stretch fracture ignored during reassembly, hydraulic lines torn by a failing pylon, slats retracting silently on one wing, a disabled stall warning, an aircraft climbing at the only speed the pilots believed was safe, but which was, in reality, 6 knots too slow for the crippled wing. The NTSB's final report concluded that the pilots had performed flawlessly. They had made every correct decision based on the information available to them. They had followed their training to the letter. There was nothing they could have done to prevent the accident, nothing they could have known that would have changed their fate or the fate of their passengers. From this tragedy came changes that reshaped aviation: mandatory review of all new maintenance procedures, stricter FAA oversight, and the end of laissez-faire delegation to airline inspectors. Redesigned stall warning systems requiring dual stick shakers on all commercial aircraft. Improved redundancy in slat position indicators and critical electrical buses. Revisions to DC-10 maintenance protocols, permanently banning the forklift method. The airline industry, as it often does, learned through loss. Painful, irrevocable loss. The lessons written into new regulations carried the weight of 273 lives, souls whose ordinary journey had intersected with a fault line in the safety system. The DC-10 would fly again, rebuilt in reputation and revised in design, but it would never fully escape the shadow of Flight 191. The public's trust, once fractured, never completely healed. And every time a pilot climbed into the cockpit of a DC-10 in the years that followed, they carried with them the silent memory of the crew of Flight 191, their professionalism, their final struggle, their unspoken warning to the generations who would fly after them. In the end, the legacy of Flight 191 is not simply a story of tragedy. It is a story of how aviation becomes safer, one painful lesson at a time, forged in the wreckage of mistakes that must never be repeated.